So let's see. Start with a new topic. Okay. So this is the 13th topic. Still modern physics. Contribution by Einstein again. Okay. Okay. Focus for 45 minutes, maybe 15 minutes. Okay. Okay. Relax. Okay, so nuclear you learned before in AS. Okay, you learn up to atomic structure, nuclear number, proton number, then end up going for neutrino, antineutrino, the particles. You know, in your A2, we call nuclear physics 50% in A2. Now here, what we will talk about? We talk about the binding energy and radioactive decay, the half-life. Half-life. Last time we learned half-life. You know what is half-life, but now with the formula. So introducing the formula. Okay. Okay. So the first thing we're going to talk about is, of course, E equals to mc squared. So in theory of relativity, I think one part comes up. Einstein is the only scientist said that energy and mass are they are related. They are two forms of the same substance. Energy can transfer to mass. Mass can change to energy, according to him. Mass and energy are interchangeable. Okay. According to him, nobody believes him. But later, of course, where it was proved, the bomb is dropped in Hiroshima. The energy is so immense, so much. Then the newspaper came out that Einstein is correct. Okay, but he never involved into the bombing. You don't want he against the nuclear bomb. Okay, so E equals to mc squared. So when mass convert to energy and energy convert to mass, where the interchange happens, not at a macroscopic level. Okay, you blast this table, it come into pieces, you collect them, the mass never changes. The mass seems to be the same at macroscopic level. But at a microscopic stage, at a nuclear level, it seems mass is lost. So it happens only at a nuclear level for time being. Okay, so mass has been found to be lost in the nuclear stage. Okay, at a nuclear stage. So I think some of you knew that during fusion and fission it happens, mass is found to be missing and replaced with energy. Okay, loss of energy. Okay, fusion and fission, you know, fusion is what? 2 marks. What is fusion? The merging of two or more fusion. Yeah, 2 or more light nuclei forms a heavy nuclear, releases energy. Okay. Okay. So fusion is a merging of 2 or more light nuclei, forms a heavy nucleus, and releases energy. Fusion. Fission, the split. Okay, the split of one heavy nucleus into 2 light nuclei, and also releases energy. Okay, fusion and fission found to be releases energy. Okay, do you have process that fusion absorbs energy? Do we have nuclear reaction which absorbs energy? Yes. Where? Yeah. Yeah. Can we say man-made? It's a man-made fusion. Man-made fission. Man-made fission produces maybe lighter nuclei become heavy nucleus. But sorry, sorry, what I'm saying. Releases, absorbs energy, right? We're talking about fusion means it always release energy. But do we have absorbs energy? Yes, man-made fusion process, especially if it absorbs energy, that means the substance forming is more unstable. Okay, become more unstable. Anything naturally occurring fusion process, if it changing, releases energy, that means new substance form is stable, more stable. So unstable becomes stable, releases energy. Okay. Unstable become more unstable, then it absorbs energy. Okay. Endothermy. Human can do that, but naturally never. Okay. Nature always go for stability. Stability means the nucleus must get more stable. So when they get more stable in the process, it releases energy. Always releases energy. Okay, fusion. Okay, so mass excess. We talk about mass excess. Okay, so so far we believe that, let's say in this case, you have one helium. Okay, I put helium. Helium 4-2. Helium made of how many neutron? How many proton? So 2 proton plus 2 neutron. Okay, so last time we thought 2 proton, 2 neutron, the mass add up will make the mass of the helium. Okay, but now scientists found that proton and neutron all are each 1 U, right? It's like 1 U. Okay, 1 unified atomic mass, right? Proton, neutron slightly bigger. But 1 U, if you write in 5 decimal places, there is a slight change, and there will be a slight change. Okay. Okay. For example, what I'm trying to tell you here is, let's say proton, neutron 4 add up, you got 4.00041. Let's say, for them. That separately total is 4.00 for U, for 1 U. Okay, I put U. Okay, when they combine, when they combine form helium, the mass must be 4.00041, but actually they found that the mass become smaller. Okay, when the nucleus form, mass drops. Some mass is lost. Okay, so the differences in this mass is called mass excess, or sometimes called mass defect. It's called mass excess, or mass excess, or mass defect. Okay, the difference in mass is called mass excess and mass defect. Okay, when this happens, mass of the nucleus is less than the sum of the masses of the separate proton and neutron. Okay, so the nucleons separately more massive. When they combine, the nucleus mass smaller than their individual masses. Okay, so this is called mass excess, or mass defect. So the mass separate proton, neutron minus mass nucleus is called mass excess. So I hope you understand this formula. The changes in the mass defect is actually the total mass proton plus total mass neutron add up minus the nucleus mass is a mass excess. Okay, so Z stands for number of proton, and stands for neutron number. Okay. More greater the mass excess means more greater the energy required to separate the nucleus. Okay, later. Okay. Okay, we will come to that energy later. So atomic mass unit, your chemistry knowledge. What is meant by one atomic mass unit? 1 U. So you have to remember the third line. Okay. Yeah, the third line. Atomic mass unit of defined as being equal to the 1/12 of mass of a carbon 12 atom. Okay. So one atomic mass unit is equal to 1/12 of the mass of a carbon 12 atom. You learned this in chemistry, right? So recall back. Okay, this topic is chemistry and physics together. Okay, so 1 U is 1.66 times 10 power negative 27 kg, one atomic mass. Okay, these are the 3 values for actual proton mass. Mass of proton, normally we thought 1 U, but if you write more decimal places, and this is how it's going to be. Slightly different. Mass of proton is 0.07276, 6 decimal places. No need to remember, in exam they give you. Okay. So neutron slightly higher. electron without no mass, negligible mass, but actually the mass is 0.000549 U. But in the nucleus stage, we don't care about mass of electron. We only care about mass of the nucleus because the reaction only happens in the nucleus. Mass changes in the nuclear process. So electron does not change. Okay, so 1 minute, try to think about the idea. How do you get this answer mentally? How do you go about this answer? So you have to use the earlier data, the proton, neutron, and electron. How do you go about calculate the mass defect of carbon 14? Carbon 14 mass is found to be this much. Calculate also the energy, or first find the mass defect first. So how do you do? How many proton, neutron it has? It has 6 proton and 8 neutron. So find the mass of 6 proton, 8 neutron separately and minus with 14.003240, right? So you get in terms of what you need, you get in terms of U, atomic mass unit.
When you memorize all the mass,
no, it will be given, but you need to know the proton and atomic number for electron, proton, hydrogen, helium. That nuclear number, proton number, you have to know. Hydrogen, helium, electron, proton, neutron. Okay, the nuclear number and the proton number, you have to remember. Expected. Other substance, they should give you the nuclear and proton number. Okay. So hope this is in your mind. So 6 proton, 8 neutron. By find the total mass minus the mass of the nucleus. This is the mass defect. Okay, mass defect when the nucleus is formed. This mass is missing. When the nucleus is forming, this mass has been missing. Okay. Then they ask calculate the energy equivalent to this mass lost. The mass which is missing equivalent to how much of energy? So we use the Einstein's formula. E equals to mc squared. So the c stands for speed of light. C is speed of light, and m is mass in terms of kilogram. This m is actually mass defect. The m is mass defect, mass change. C speed of light. Right? You should remember, right?
How many decimal places you should put? 6 decimal places.
For the mass to get mass defect, you need to use the entire decimal places.
So everything on
everything? Yeah.
Or just
the mass defect will be very small, so you have to consider all the decimal places. You never consider all the decimal places, you won't get differences. So first, what you need to see, the mass must convert to kilogram. So you times with 1.66 and 10⁻27. The U have to change to kilogram. Then speed of light. Then you get in terms of what you need. You get in terms of joule. You get in terms of joule, right? Then you should know how to convert to EV. Here they want in terms of EV. Joule to EV, EV to joule. You should know in these two topics. So EV change to joule, you do what? Times with 1.6 times 10 power of -19, and the other way around, divide. Joule or electron volt, big unit for energy. Which is big unit for energy, joule or EV? Joule. Joule is a very big unit. EV is a very small unit for energy, used for subatomic particle. Yeah. So under 2 mega EV. This is the energy possessed by the mass which is lost. Okay. So hope you have these ideas in your mind. Normally they ask in terms of EV or most probably mega EV. Okay, I think shouldn't be a problem. Okay, binding energy. Okay, every nucleus has binding energy. Okay, what is meant by binding energy? So yeah, the fourth point. Binding energy is defined as the energy required to completely separate the nucleons of a nucleus to, please add, to infinity. To infinity. Please add infinity. To infinity, one pass here, they give 1 mark. Okay. So what is binding energy of a nucleus? The amount of energy required to separate all the nucleus to infinity. Proton, neutron, have what type of force between them? They have a strong nuclear force, weak nuclear force, which hold them together. Strong nuclear force is very strong it's a short range. So the amount of energy to separate them, all of them, to infinite, the amount of energy needed is called binding energy. Okay. So greater the binding energy means the nucleus is more stable or less stable. You need lots of energy to separate them. Most probably more stable. Okay, more stable. Okay, I'll come back to the stability. More binding energy means most probably it's more stable, but it could have lots of nucleons, therefore more energy required. Okay, so not really correlate. Most probably it's more stable. Okay. Okay. So remember, when separated nucleons are combined to form a nucleus, the same energy will be released. Okay, you split them, you use 10 eV. Then when it merge, 10 eV will be 10 mega eV will be released. Okay, so you get back that energy. Okay. So when you split, you supply energy. Okay, you use your own energy to split them. The energy done tend to become what? Tend to become mass. All the particle gain mass has been added. Okay, when you supply energy, okay, split them, it tend to become mass. Okay, and they form, mass is lost, give up the same energy. Okay, so when the nucleus is formed, energy will be released. Okay, if it's a stable nucleus, from less stable to stable nucleus formation, energy, there will be a net energy will be released. Okay, will be energy released. So the energy is same. To split and to form back, the amount of energy is called binding energy. Only thing you need to know, is it releasing or absorbing? Okay. And when you split the nucleus, energy has been absorbed and changed to more mass. Okay. So that is binding energy. What is binding energy? The amount of energy required to split all the nucleons separate to infinite from the nucleus. Okay. We have another term, something called binding energy per nucleon. Binding energy per nucleon. For example, let's say you have uranium, you have carbon 12, carbon 12, uranium. What is the nucleon number? 285. 200 plus, around 285, I think, the nucleon number. Carbon 12, the nucleon number is 12. So uranium and carbon 12, uranium has more nucleons. Okay, it's a big nucleus. Okay, carbon is only carbon 12, got only 12 nucleons. Okay, uranium found to be, which will have more binding energy? More binding energy. Uranium most probably will have a more binding energy because more nucleons need to be separated to infinity. But does that means uranium more stable? Carbon is more stable. So more binding energy means we can't really say it's more stable. Most probably going to be stable. But the more better term to check, is it more stable or not? Checking binding energy per nucleon. One nucleon got how much of binding energy? That shows stability. That means what do you do? Let's say the uranium got X EV, the X EV divided by 285, and carbon maybe you have Y EV divided by 12. I think carbon will have a greater binding energy per nucleon, more stable. Okay, what is binding energy per nucleon means? The formula here. Binding energy of the nucleus divided by the nuclear number. Nuclear number.
Higher binding energy is
more stable.
more stable.
You need lots of energy to separate them. You can't simply cannot separate them. Lots of energy required to separate one nucleon to another. So what makes stability for a nucleus? Binding energy per nucleon. Okay. But I've seen all the mark scheme in the Cambridge, most of the mark scheme. Why it's more stable? The answer mark scheme say because it has more binding energy. Okay, they never say binding energy per nucleon. To be correct, binding energy per nucleon. Mark scheme put always because it has more binding energy. Okay. So it's very difficult for me to say here. You better say if a nuclear number is not given, you say more binding energy. Okay, one example, come on. 1 minute, no need to do the entire calculation. Give a rough idea. Think how do you go about this question in your mind, working. Okay, the question asking for how do you find the mass defect? Mass defect. So yeah, the nuclear number minus the two proton plus the 2 neutron mass minus the mass of the helium, right? Mass of the helium. So proton, 2 proton times this, 2 times this minus this, you get the mass defect. Okay, no problem. What answer you get in terms of U? In terms of U. How do you get binding energy? Binding energy use E equals to mc squared, but we got some working to do. The answer above is in terms of U, so you have to convert to kilogram first. So how do you convert? So times with 1.66 times 10 power of negative 27. Unified atomic mass. U change to kilogram times. Okay, 1 U is that much of kilogram. If you let's say you got here 0.8 U, then 0.8 times this you get in terms of kilogram. Then you must put into here in terms of kilogram times speed of light square. You get the answer in terms of joule. Idea, remember? 1.66 times 10 power negative 27. Will be given the front page, right? Unified atomic mass to be used. Okay, so that's the structure, must be in mind. Next, see how do you find binding energy per nucleon. So whatever energy you got here, what do you do? You divide by the number of occupants, nucleons. So how many nucleons in helium is 4. Don't take proton number, nucleon number. So divide by 4, you get the binding energy per nucleon. Okay. So yeah, so this is the rough working, right? I think this should be in your mind, the working. So 2 times 2, 4.03188 minus with the nuclear number, you get the mass defect. Then mass must change to kilokg times with the U and speed of light square, get joule. The answer given here in terms of EV. Okay. So question never they never tell EV or joule. Okay. Normally it will be EV. They say energy. Then you go down, you see the marks, the dotted line, the answer section, they put EV. So you have to convert to EV then. So joule change to EV here by 1.6 times 10 to the 19. So EV, preferably change to mega EV. Mega EV divide by 10 to the power of 6, right? Your conversion, conversion. Then divide by 4, so you get per nucleon, binding energy per nucleon. Okay. Okay, so let's see. Move on. So this answers. Okay, this will hold on. Go back to this hold on. Okay. Go to this slide first. Okay, so scientists did experiment with all the nucleus, finding binding energy per nucleon for all of them. They were quite surprised to see a graph like this. Okay, a graph what versus what? Binding energy per nucleon versus the mass number or the nuclear number. The nuclear number. Okay. So they found the graph goes up and comes down. So they found the most stable element is iron. Okay, iron is found to be the most stable, not element, the most stable nucleus. Okay, it's iron. Electron configuration is not bad, not that stable. Chemistry, iron is really can rust because electron configuration not stable. Electron can move around, but the nucleus is always stable. Okay, in under chemistry we never learn about nucleus. Silver going to be always silver for billion years. Gold will be always be gold in billion years. That's chemistry. We never really talk about the nucleus is transforming. Okay, here physics we talk about the transformation of the nucleus. Okay, theoretically what I see, you buy a gold of 1 kilogram now today. Okay, after a few billion years later, maybe billion years, the gold might change to other material, other type of material, because which is the most stable one? Iron. So naturally, all nucleus want to achieve stability, so they plan to go for iron. Okay, but the process of changing from one nucleus to another, okay, there will be an intermediate atom, lead. Okay, convert to lead. Lead to convert to iron. Lead itself takes few billion years. The half-life of iron, half-life of lead is so very high until it exceeds the time taken for the formation of our universe. Okay, our universe formed about 13.7 billion years ago. Okay, Big Bang. 13.7 billion years ago, it's predicted, and the lead half-life is more than 13.7 billion years ago, or more than that. That means theoretically, is it going to reach iron? Half-life of lead is stronger, so most probably all going to stop at lead. By the time it go to iron, I think I don't know what happened to our universe. Okay, it's a very long period of time. Okay, so in exam, if they ask what is the most stable element, iron, Iron Man. Okay. Oh, it can rust, but nucleus never change. Okay, nucleus is going to be stable. Okay, the most stable nuclei can be found in the peak of the curve, which correspond to the element iron. Please remember another one extra element. Please remember the nucleon number of iron. The peak is 56. Okay, because one year they draw the graph, they asked you to plot where's the element of nucleon number of 70 lies. Draw a mark point. 70 nucleon number. Element with 70 nucleon number. Mark a point. So it should be after the peak to the right. Okay, the peak is 56 nuclear number. So you must mark a point after the peak. Okay. This no need to get this. I ignore this graph. This graph is mass per nucleon with the mass number. You're going to convert. Just remember this, the earlier one. Okay, this graph is important. Okay. Okay, this graph I need to talk more about. So because uranium is not stable compared to iron, so uranium target is to reach to become iron. So what will happen? Fission or fusion? Fusion will happen. Fusion. So the region here, all the substance will experience fission, they split. All the small elements here, which is hydrogen, they can fusion to achieve iron. Yeah. So this is what happening naturally. Okay, worldwide, all the substances are fusing, radiating. Okay, want to achieve stability. Okay. Okay, so AS, nuclear fusion, not much to know in AS, but in A2 you have to know in depth about fusion. So fusion experienced by a lighter nucleus, undergo nuclear fusion under certain conditions. You need a certain condition, not simply going to fuse. Hydrogen not fuse on the surface of the earth because of what? We need a very high temperature, million degrees Celsius. Sun, the core is million degrees Celsius. Fusion happened, high pressure. So the energy radiated to the surface found to be about 5,000 degrees Celsius for the sun. Okay. Fusion never happens at the surface of the sun. Fusion happens at the core of the sun. The core. Hydrogen managed to merge. Okay. So fusion under certain conditions only need very high temperature, 1 million degrees Celsius for hydrogen. For helium to merge, need even higher temperature. Okay, even give more energy. Our sun, hydrogen merge form helium. Then helium and helium unable to merge for our sun predicted because not much of pressure. Okay, a sun like more maybe 10 times bigger than our sun. Maybe in that core, helium can merge form, can fuse to give more energy. Okay, black hole, I think it converted to iron, and even iron cannot withstand the pressure, high pressure, because very huge sun, gravity is so strong. Even the iron will be destroyed, the nucleus, right? The even electron will collapse to the nucleus. Okay, so it can't form atom anymore. The black hole, no atoms, all are subatomic particles. Okay, neutrons, they can't form nucleus because so much of pressure. Okay. Okay, so in general, nuclear fusion possible long as the final product has more binding energy per nucleon. So remember, naturally occurring process all go to a more stable element, naturally occurring process. Okay, not man-made, naturally occurring. Okay, in exam when you see an equation on top, don't think it's going to be a exothermic. Okay, it could be a man-made process. They won't tell you. You have to see the equation. Okay. They will tell you it's an energy release or absorb. Okay. So energy if released, it's a naturally occurring process. Sometimes it could be endothermic. If it's an endothermic process, then reactant or product more stable. Reactant more stable. If it's a endothermic process. Okay. Endothermic is good or bad for us, for human. You do a nuclear process, the process is found to be an endothermic. You are giving energy to it, changing the element to more unstable. Is it benefit for human? No, we want energy from the nucleus. So we always want exothermic. Okay, but man still do some element become endothermic. They produce some unstable nucleus for certain purpose. I think for medical reason to inject that one substance ionizing radiation what do you call a nucleus into the bloodstream to find what do you call cancer cells to catch the cancer cells. The type of injection they do is a radioactive element which made by human, very unstable, maybe about I think I think 1 or 2 hours the half life. So when they inject into the body, it goes around wherever there is a what do you call cancer cells are there. It's surrounding it. You give out rays, gamma rays out of the body, from your body, okay, from the patient body. So when they use scanners scan your body, it forms white spots wherever there is a cancer cells. Okay, so white spots appears, bright spots appears on the screen. That means there is a cancer cells. Okay, so yeah, man-made can produce an element which is endothermic but unstable, and that is for a medical reason. Okay, the enormous amount of energy generated in the sun. Of course, the only place where we know fusion happen is, of course, sun. So in sun, hydrogen and hydrogen merge form a helium. Lots of energy is released. Yeah, energy released in the fusion process very much greater than the energy release. This is one good point. Okay, why? Okay, you have 1 kilogram of hydrogen. You have 1 kilogram of uranium. Okay, uranium undergoes fusion. 1 kilogram of hydrogen, let's say, undergoes fusion, but the amount of energy comes out, fusion is more than fission. Okay, why? Anyone? Why? Because hydrogen, the mass, what do you call the mass of one atom of hydrogen is very small, 1 U, right? 1 U, but uranium is 285. So 1 kilogram of uranium, 1 kilogram of hydrogen, which will have more nucleus. Hydrogen will have more nucleus. Okay, so one nucleus is only 1 U. Okay, one hydrogen is made of like 1 proton, right? 1 U. This is 285. So here uranium number of nucleus is limited, very small. Maybe, I don't know, maybe 1 million. Here 1 kilogram of hydrogen might have 10 billion of nucleus. So you see, number of fission reaction is 1 million. Here, fusion reaction, number of fusion reactions, 10 billion maybe. So the amount of energy comes out is small for the fusion. Reason is what? The number of nucleus. Okay, the number of nucleus per kilogram. Okay, the number of nucleus per kilogram of hydrogen is greater. Okay, the number of nucleus is greater compared to uranium. Okay, for the same mass, because the nucleon number is small for hydrogen. That's why more energy is released. Okay, they found one uranium reaction release more energy than one hydrogen reaction, but still fusion give more energy because more nucleus. Okay. Okay, an example of nuclear fusion is due to deuterium atoms fused together to form a helium-3 under extremely high temperature. Actually, in sun, not only this one process, I think 2 or 3 process finally end up to helium. Hydrogen merge to deuterium, and deuterium merge with another hydrogen. I think the third process will give you helium. Okay, so whenever you see this equation, hydrogen change to helium, so mentally you should know it's a fusion process. Okay, so next, if you see this equation, this is a fission process. How do you know? They bombard with neutron, and its uranium 235 tend to become smaller nucleons. Lighter nuclei. Big nucleus become smaller nuclei. So this is fission, splitting. So an exam, roughly you should figure out, is it fusion or fission? Okay, checking the nuclear number. Lighter nucleus become heavy nucleus is fusion. Heavy become lighter is fission. Okay, so heavy nucleus disintegrate into lighter, more stable. Fission fragment have a greater binding energy per nucleon. Okay, fission fragments, the final product normally will have a greater binding energy per nucleon. Unstable becomes stable. Stable will have greater binding energy per nucleon. Okay. Okay. So one question. Okay, so we're going to calculate the energy release again. How much energy released? Okay, so what process? Fission or fusion? See the equation alone. It's a fission. Heavy nucleus become lighter nuclei. Right? 2,3 uranium, 236 absorb neutron, 235, sorry, 235 absorb neutron become 236 uranium, then split into a small lighter nuclei. This is the intermediate stage. 236 is unstable. 235, okay. Suddenly a neutron is absorbed, the nucleus become very unstable, they split. Okay, fusion happen. Need technology for that. I think you have two types of uranium. The uranium commonly found in the, I think more than 90%, 238 or 235. Check from the internet. Uranium, which uranium really in the Earth crust, majority in form of 238 or 235. The nuclear number 238. 238. Okay. 238 uranium is the most found on the when they got it, it will be in form of 238. Okay, but the one used in the nuclear bombs and everything is 235. 238 is useless to do bomb because it's not fissile. 238, you send a neutron, it won't become unstable. So 235, you send the neutron, become 236, it become unstable, it breaks. That's what the research found. So what they do, some countries do enriching. We call enriching uranium. Enriching uranium is a process of changing 238 to 235. If any country changing 238 to 235, enriching uranium, enrichment only can done for two purposes. One for nuclear reactor, another one nuclear bomb. Okay, so that's why US really alert. So any countries enriching uranium means you can't do that. Okay, the country will say I'm going to use for the nuclear reactor, but they can't use it for nuclear bomb and enrichment. Okay, so let's see this question. So the 236, the binding energy per nucleon for each products as given by this is the binding energy per nucleon for 236, 146, 87. Identify X and Y and complete the equation. Okay, first, get me what is X and Y represents. What type of element? Use your AS knowledge, balance the nucleon number, proton number, figure out what is X and Y should be. Yeah, nuclear number, proton number, conserved, right? What are the things conserved in nuclear reaction? Proton number, nucleon number, proton number. What else conserved? Momentum is conserved. What else? Mass energy together conserved. Okay, so four things conserved. There are many actually, but in your syllabus, nuclear number, proton number, momentum conserved, mass energy conserved. Mass energy together is conserved. Okay, so what is X and Y? So 236, we no need to look at this. We just go straight to 236. 236 become this. 236, so what is X? Neutron. X is neutron. So X is neutron.
Y is gamma ray.
One neutron is 1? 1, 0. This number you have to remember. So Y, I think Y should be gamma ray because I both gives you 0, 0. So we blame the gamma. Gamma ray. Can go for gamma. So X is neutron and Y is gamma ray or gamma photons released. Okay, so remember the neutron, proton, hydrogen, the nucleon proton number arrangement, and helium. Sorry. Okay, next, name this type of nuclear reaction. So it's a fission process. Explain why the neutrons are used to split uranium-235. The question here they're asking, why neutron? Why not electron? Why not proton? So why neutron? Everyone knows why. The neutron easily can get into the nucleus without any repelling force. Okay, easily accepted by the nucleus. Okay, because no repelling force. So answer is neutron because it's neutral. It's neutral, so no repelling force, easy to be absorbed by the nucleus. Okay. Why not proton? Repelled by the nucleus. Why not electron? Also repelled by the electron cloud. Electron, not even can reach the nucleus. Before he reach the nucleus, the electron will repel it. Okay, so 3, explain why neutrons. Okay, we're done. B, estimate the amount of energy release. This is what my main focus in this question. How do you find energy release in this equation? Okay, how do you find energy release? E equals to mc squared. You find the mass defect. Okay, mass defect. Tell me, mass of reactant big or mass of the product big? This is it's a fission natural. We can say energy is released normally. Yeah, energy is released. So which mass is big? Reactant big or product big? Reactant should be big, more mass. When come to product, energy has been released. From where the energy got, some mass has been lost. So product must have less mass. Okay, less mass, some become energy. So yeah. So explain why the estimate the amount of energy release. But now the problem is all the values not given 5 decimal places. So you can't find the mass defect. You can't. How do you estimate 5 decimal places? So sometimes they give this information. You have to use this information to calculate the energy release. Okay, how do you find this energy? This is binding energy per nucleon. Okay, binding energy per nucleon. Okay, first one, binding energy for uranium per nucleon. If you know per nucleon, can you find binding energy of uranium? Just times with 236, you get a binding energy of reactant. Then you can find binding energy for product also. Okay, which binding energy should be greater? Which binding energy should be greater? The total binding energy. The product or reactant. Product must have greater binding energy. Good. Why? More stable. It is more stable, will have greater binding energy. What is binding energy means? The amount of energy required to split all the nucleons to infinity. So you get all the binding energy from reactant and product. So how do you find the energy release? The total energy of product minus the total energy of reactant. Total binding energy of product minus the total binding energy of reactant, you get the energy release. Better go for product minus reactant.
Always use product minus.
Yeah, product minus reactant. Total product binding energy minus the reactant. Always, yeah.
184.
But here, do neutron has binding energy? In exam, they ask why neutron don't have binding energy. It does not bind to anything. It's a standalone particle. It's a one single particle, so it does not bind with any other particle. So therefore, it don't have binding energy. Single particles don't have binding energy. Okay, binding means you need to bind with another atom, then called binding energy. Yeah, one day they asked why the neutron all not included in the calculation. Why they don't have binding energy? Because it's a single particle which does not bind with any other particles. Therefore, it don't have binding energy. Energy loss happens because the differences in the mass. The total mass might be lost because the neutron later will be absorbed into the nucleus, so there will be a mass change. But the neutron alone don't have any binding energy. Okay, the mass difference causes the energy loss. Okay, next, estimate the amount of energy release. So that's how you calculate. Let me show the answer. So hope you understand. So this is the answer given. Any part you don't understand? First, the first one. So neutron, gamma, photon, or gamma ray do nuclear fission. We know that because heavy nucleus become lighter nuclei. So it's a fission. And neutron I use because electrically neutral. And C is the part C, that's important. Okay. So they're getting binding energy for the product. Product is the total product binding energy, is the total reactant binding energy, both subtracted. The differences is the energy release. This is the energy release. Okay, then ask how this energy release, in what form? In form of heat. In form of heat, of course. Energy is released, energetic photons, kinetic energy of neutron later appears as heat, heat energy. As I said, nuclear bomb, Hiroshima, when they dropped, 150,000 people died, 80,000 people died just immediately because of what? Because of heat. Heat make them just vanish, just become vaporized. Okay, just disappear, become vaporized. 80,000 people within 1 kilometer. Okay, so very strong. Hiroshima, the heat is very, very strong. Okay. So we stop here. So we discuss tomorrow.